Hello. In the previous lecture, we talked about the internal energy E and the enthalpy H of a system. We also derived a number of equations for the change of these properties in relation to the temperature and pressure using the first law of thermodynamics. In this lecture, we will first define isentropic flow, and then, using thermodynamic principles, we will derive the isentropic relations and the energy equation. These equations will enable us to calculate velocities, pressures, densities and temperatures in compressible flows. But first, a few definitions. When we have a process with no heat addition or extraction, we call it adiabatic. When in a process there are no frictional or dissipative effects, we call this process reversible. A process which is both adiabatic and reversible is called isentropic. In the previous lecture, we talked about the first law of thermodynamics for a reversible process. dE is dQ minus P dV, where V is the specific volume. Since dQ is 0 for isentropic flow, the first law of thermodynamics transfers into dE is minus P dV. When we introduced the term enthalpy, H, in the previous lecture, we found dQ is dH minus V dP. With dQ is 0, we get dH is V dP. And then we introduced the specific heat coefficients CV and CP and found dE is CV dt and dH is CP dt. Now, these two can be combined with the two for the dE and dH we already have, and so we have CV dt is minus P dV and CP dt is V dP. When we divide the first by the second equation, we find dP over P is CV over CP times dV over V. We now define the ratio of specific heats, Cp over Cv, to be gamma. For air below 600 Kelvin, gamma is 1.4. So we have found dP over P is minus gamma times dV over V. If we integrate this equation along a streamline between points 1 and 2, we get the integral from 1 to 2 of dP over P is minus gamma times the integral from 1 to 2 of dV over V. So the integration gives ln, the natural log, of P between stations 1 and 2 is equal to minus gamma times the ln of V between 1 and 2. Using the rule for subtraction of logs, we find ln of P2 over P1 is minus gamma times the ln of V2 over V1. We can also write this as P2 over P1 is V2 over V1 to the power minus gamma. And since V is 1 divided by rho, finally we have found for isentropic flow, P2 over P1 is ρ2 over ρ1 to the power gamma. Now, this relation between the pressure and the density can be very useful when we deal with compressible flows, but we would also like to relate, for instance, the pressure and the temperature between 2 points along a streamline. There is already an equation that relates the pressure and temperature in one point, and that is the equation of state. So we're going to use that to transform the equation we already have. From the equation of state, we know that ρ is P over RT. If we replace ρ1 and ρ2 by P1 over RT1 and P2 over RT2, then we find P2 over P1 to the power 1 minus gamma is equal to T1 over T2 to the power gamma, or written differently, P2 over P1 is equal to T2 over T1 to the power gamma divided by gamma minus 1. The same can be done with respect to the relation between ρ and T. This way we have found a set of isentropic relations which we can use in compressible flow. Now, in aerospace engineering, we are also interested in how the velocity changes with temperature and pressure. So it would be nice to have a relation between the change of the velocity with at least one of the three properties in the isentropic relations along a streamline. And there is one, called the energy equation. In the following slides, we will derive the energy equation using the Euler equation, yeah, him again, and the first law of thermodynamics. Okay, earlier we found that for an adiabatic process, this first law can be written as dH minus VdP is 0. Inserting the Euler equation, dP is minus rho V dV, gives us dH plus V rho V dV is 0. Now we know that small v, the specific volume, is 1 over rho, so we get dH plus V dV is 0. Also here we will perform an integration between the stations 1 and 2 on the streamline. So the integral from h1 to h2 of dH plus the integral from v1 to v2 over v dv is 0. And this is h2 minus h1 plus a half v2 squared minus v1 squared is equal to 0. And rearranging gives h1 plus a half v1 squared is h2 plus a half v2 squared, and thus h plus a half v squared is constant. Perhaps you can recall that earlier we found h is Cp times T, in which Cp is the specific heat coefficient at constant pressure. So finally we have Cpt plus a half v squared is constant, the energy equation. Note there is no rho between the half and the v, like in the Bernoulli equation, a mistake that easily can be made. And so, summarizing what we have found, for incompressible flow we have this set of equations, the continuity equation in the incompressible form, A times V is constant, Bernoulli's equation, P plus a half rho V squared is constant, and of course the equation of state for a perfect gas. For isentropic compressible flow, we have found 4 equations. The continuity equation in the compressible form, rho AV is constant, the 3 isentropic relations with gamma is Cp over Cv, the energy equation, Cpt plus a half V squared is constant, and also here the equation of state of a perfect gas. I say we are well prepared to tackle compressibility problems. In the next lecture we find ourselves right in the middle of that, as we will treat the speed of sound and the Mach number.